It is Gateway Week. Today is, what, Monday the 19th of September. So your Gateway exam is Friday, the 23rd. It will be the second half of class. We'll have a half a class that day on Friday. The second half of class, you'll have the Gateway exam. I should be able to grade the Gateways pretty quickly and let you know your score. Do study for them, okay? Again, we want to try to get better than that 50% rate, passing rate that's happened in the past. We can do it if we work hard enough. And work on both remembering certain integrals and remembering techniques and practicing them to make sure we don't make mistakes. Two pretty different topics in lectures A and B today, though all ultimately related to integration. Lecture A, I'm going to talk about differential equations and integration by partial fractions. I will apply integration by partial fractions to help us solve a differential equation. And in lecture B, go back to parametric curves and vectors, and I want to get further this time. I'm not going to go over the next Mathematica assignment, though you will have one for Wednesday. I'm not going to go over it so we have more time to talk about the content. And see that we come up with integrals that are pretty hard to do oftentimes, and so we have to rely on something called numerical integration. So I'll introduce that today, though you've already done that to some extent with left and right hand sums and their averages. All right, so differential equations. You've already read about differential equations a bit, or you should have, in section 6.3 as part of the review for the mini exam. And I did put a differential equation problem on the test. I made it be a fairly easy one, something I call a pure antiderivative problem. We've got an equation in the form dy dx equals some function of x. Let me pick sine x plus x squared. That's an example of a differential equation. Differential meaning it's got a derivative. As you know, differentials are related to derivatives. And it's an equation. Solutions of differential equations are not numbers, they're functions. We're looking for, in this case, all the functions that satisfy this kind of equation. And like I just said a minute ago, this is called a pure antiderivative problem. All you have to do to solve it is just integrate. You're looking for a function y with a function of x whose derivative is always equal to that. So we define the indefinite integral of sine of x plus x squared. The general indefinite integral will be negative cosine of x plus x cubed over 3 plus c. And that family of functions, one function for every value of c, is called a general solution of the differential equation. Circle it. Y equals negative cosine of x plus x cubed over 3 plus c. That would be a general solution of this. Infinitely many possible different answers for the infinitely many choices of c. If I add something called an initial condition, add an initial condition is what I'm writing here, that I want y of 0, in other words, the y value of this function when x equals 0, to be, say, 4, I can solve for the value that c must be. Use this condition along with the fact that that's the general solution to solve for c. We want 4 to equal negative cosine of 0 plus 0 cubed over 3 plus c. Cosine of 0 is 1, so this becomes a c minus 1. Solve for c, c must be 5. That then generates one unique function that solves both the differential equation and the initial condition. Together, these make up something called an initial value problem. A differential equation and initial condition make an initial value problem. Your unique solution of the initial value problem, which I abbreviate IVP, is y equals negative cosine of x plus x cubed over 3 plus 5. Infinitely many solutions make up the general solution. One solution, one function makes up your unique solution to the initial value problem. When your differential equation just has x on the right-hand side, it's dy dx equals something involving x, that's a pure antiderivative problem. But differential equations usually aren't that simple. I'm going to put something else on the right that will look simple, but it makes the differential equation conceptually more difficult. dy dx equals, let's say, 3y. So you might look at that and wonder, that's a little weird, strange looking. Find a function whose derivative with respect to x is 3y. What would that be? 3xy? 3 halves y squared plus c? No, it's neither of those things, okay? What you're really after, it's probably better to use function notation, it's just not as traditional, is a function f of x whose derivative is always 3 times the function. That's what you're looking for. Y represents the function f of x. It would be better to write it this way, but this is more traditional. Sometimes people also just write a y prime. What function is there whose derivative is 3 times itself? Well, how about e to the 3x? That's one example. Or how about 2 times e to the 3x? Both of those functions would have a derivative equal to 3 times themselves, because you bring down the 3 with the chain. Because the derivative of the inside function, 3x, would be 3. So the general solution here actually turns out to be y equals c times e to the 3x for any c. Can that be derived without guessing? Yes, you can use a method called separation of variables to derive that without just guessing. It's easy enough to guess in this case. What you can do is do the thing that I said oftentimes is an okay thing to do in calculus, even though it's not mathematically rigorous for us, is pretend that dy dx is a fraction, even though you should have probably had a teacher in the past who told you it wasn't. It's a derivative, it's a derivative. It's not really a fraction, it's a limit of fractions, but it itself is not a fraction. However, it doesn't usually hurt to pretend it's a fraction. And put the dx over on the other side. Oops, dx. And then divide both sides by y to get the y on the left side. So write dy over y equals 3dx. It's a little strange. Physics teachers do this all the time. Okay, your physics professors, they do this kind of thing all the time and they don't worry about it. Engineers do it all the time, chemistry teachers. Is it mathematically valid? Well, it can be made so, but it gets complicated, okay? You've got to do some pretty advanced math. There are a couple different ways you can approach it that's pretty advanced to justify thinking of those things as fractions. But for us, it's just symbol pushing. When you see something like this, you should want to integrate both sides. It's almost like you should get this irresistible urge to integrate. Go ahead and give in to that urge and put the integral signs in there. And now do those integrals. On the left, you get the natural log of the absolute value of y plus c, but I'm going to put the c just on the right side. And on the left, you get 3x plus c. I'll call it c1, for a reason you're going to see in a minute here. So I integrated both sides after the separation of variables. Now the goal is to solve for y in terms of x. Exponentiate. You get the absolute value of y equals e to the 3x plus c1, and by a property of exponents, that's e to the c1 times e to the 3x. And treat this essentially like your c. Can I get rid of the absolute value signs? It turns out you can. Okay? It turns out if you get rid of the absolute value signs on the left, replace the e to the c1 with just a c, that certainly is a general solution. This will be a solution to that differential equation no matter what c is.
So hold on. So what you were just doing with treating the derivative as a fraction, is that just proving that the general solution is correct?
No, it's deriving it. To prove that this general solution is correct is actually easier in a sense. All you have to do is differentiate it and see that you get 3 times itself, which is obvious because of the chain rule. When I differentiate this function, I get an extra factor of 3. In other words, I get 3 times the function. That's why. So verifying that a function solves a differential equation like this, once you know what to do, is actually very easy. You got to know what to do though. You got to check that the left-hand side and right-hand side simplify to the same function of x. Question?
Would it be fine to leave it as e to 3x plus c, or should you have it c?
The c should be in front. Oh, well, okay. I was thinking about this would be wrong.
Right.
Okay. This technically is a solution for any value of c. However, it does have a defect in that it doesn't give you solutions that go negative, which this one does, if c is negative. And you want to possibly include those.
Right.
So there's your general solution. If I add an initial condition, y of 0 equals 5, for example, then I can take my general solution, solve for c. In this case, c is 5. So the unique solution would be y equals 5 e to the 3x. That would be the unique solution of the initial value problem, the differential equation, and the initial condition. Here's the general solution of just the differential equation. Infinitely many answers for the infinitely many different choices for c. This one function is the unique solution of the initial value problem consisting of both the differential equation and the initial condition. What kind of application does this have? This kind of differential equation has an application to exponential growth. The solution is an exponential growth function. Okay? So the simplest kind of growth is exponential. That's the way to model growth with the simplest kind of function. Doesn't mean it's a perfect model, but it's the simplest kind of thing to do that's reasonable in many situations. And the differential equation is essentially saying the rate of change of the population is proportional to the population itself. If you think of x as time, I could call it a t instead. The rate of growth, say in thousands of rabbits per year, is proportional to the number of rabbits. The more rabbits there are, the more babies are going to be born. Okay? Of course, rabbits are going to die because of overcrowding, perhaps. But that's what we take into account with our next model. And with this one, that's where we're going to use partial fractions. Do you have a question? That was the exponential growth model. There's something else called the logistic growth model. Oftentimes this feels a little bit backwards because both with the exponential growth model and this logistic model, we basically know what we want the graph to look like ahead of time. With the exponential growth, it's just, it's increasing in concave up, ultimately growing faster and faster over time, very rapidly, in fact, because it's exponential growth. With the logistic growth, the population, I think I'll call the population P this time, and call the independent variable T for time. We want the graph to basically look like this. We want it to be sort of like an exponential growth here initially, increasing in concave up, but after a certain point, it'll become concave down. There's an inflection point, and look like that. Will it have a horizontal asymptote or not? Okay, maybe, maybe not. Increasing and concave down functions sometimes have horizontal asymptotes, sometimes they don't. Turns out in this case, we actually do want a horizontal asymptote. We want there to be a limit to how big the population can be. The idea is at some point there's going to be overcrowding. P might be a population of rabbits. Population of rabbits, for example, in some ecosystem, maybe in thousands. It seemed like there were thousands of rabbits in our yard this summer. They were everywhere. Lots of rabbits this year. No, there weren't thousands, but some ecosystems, maybe there's a limit to how many rabbits can be living because of limited food, limited space, that kind of thing. Maybe it's 5,000 rabbits. Since the rabbit population is in thousands, would be 5,000 rabbits. And this might be time in years. So essentially we know what the graph should look like. Again, this is kind of backwards. Now we're going to write down a differential equation that hopefully has that kind of graph as a solution. Okay? It's not always done this way. It's not always an approach where you say, okay, let's figure out what the graph looks like, then what should the equation look like? Oftentimes it's what is the equation first is figured out, and then you figure out what the graph looks like from that. What kind of equation, what kind of differential equation would give us a solution that looks like that? Well, let me basically just tell you the answer, and I'll explain why this is a good idea after I write it down. There's going to be some constant k times p times 5 minus p on the right-hand side, or some constant k, which is bigger than 0. I tend to make my little k's cursive because they look too much like big K's when I make them not cursive. Why is this a differential equation that might have functions like this as solutions? If p is close to 0 in value, if the population is low, then 5 minus p is close to 5. And the differential equation, you might say, is approximately 5k times p, a constant times p, like exponential growth, like that other example, dy dx was 3y. The right-hand side is a constant, or approximately a constant, times the dependent variable p in this case, instead of y. Because this is close to 5, is the intuition. However, as the graph grows initially exponentially, it heads toward 5 in value. This quantity gets closer and closer to 0. This quantity is not getting closer to 0, but this one is. Making dp dt get ultimately closer to 0. And that's what you see happening. When the graph is leveling off, the slope is getting closer to 0. In fact, when p equals 5, if the population was at 5,000 to start with, that would be 0. The whole thing would be 0 on the right. You'd be looking for a function whose derivative is always 0, a constant function. In fact, the constant function 5 would work. If the population starts out at 5,000, it's going to stay. What does that mean practically? It means babies are being born at the same rate that other rabbits are dying. So of course it varies a little bit, but the idea is that it's basically constant. How do you solve that kind of differential equation? Can we find a formula for the function that looks like that? The separation of variables technique works. Go ahead and pretend dp dt is a fraction and pretend you multiply both sides by dt, getting the dt on the right. Get all of this stuff except for the k, the stuff involving the p's, on the left. That's the separation of variables. Separating the p and the t to different sides of the equation. The k is kind of irrelevant as far as which side it's on. It's going to look like this after separation of variables. Got all my p's on the left and all my t's on the right. Now, again, you start to get the urge to integrate, so go ahead and integrate. That integral is easy to do. Kt plus c, maybe I should call it c1. Maybe it won't be my final c. What about the integral on the left, though? That looks harder. It's a partial fractions problem. Here we go with partial fractions. The function we're trying to integrate is 1 over p times 5 minus p. It's a function of p. Is there some constant a and another constant b where this is true? When you have linear factors in the bottom like this, there will be. And now it's just our job to figure out a and b. Multiply both sides by the common denominator there, p times 5 minus p. It completely cancels on the left, leaving you with a 1. On the right, you get partial cancellation. The p cancels with the a term, leaving you with a times 5 minus p. And the 5 minus p cancels with the b term, leaving you with b times p. You want this to be true no matter what p is. So go ahead and plug in special values of p to make it simple to solve. Like p equals 0, you get 1 is 5a plus 0, so a is 1/5. When p is 5, you get 1 equals 0 plus 5b, so b is 1/5. Plug those in, get 1/5 over p plus 1/5 over 5 minus p, and those are both easy to integrate. You're going to get logarithms, just like the examples last time. You do have to be careful in integrating this one, though, because that minus sign down there in front of the p, you're going to get an extra minus sign when you integrate. If you want to think of it as a substitution, w equals 5 minus p, dw would be negative dp. This kind of problem, by the way, comes up on the gateway, integrating this kind of thing. Let's do it over here. So integrate 1/5 over p, you're going to get 1/5 natural log of the absolute value of p. P is going to end up being positive, so we'll be able to get rid of the absolute value signs. Careful, minus. There's a plus there, but I get the minus, like I mentioned a minute ago, from integrating that. Minus 1/5 natural log of the absolute value of 5 minus p. Actually, 5 minus p is going to be positive for this kind of solution as well, because p is going to be between 0 and 5. Though if p was bigger than 5, if the population started out higher than the carrying capacity, then the brackets would die off toward 5, and the 5 minus p would be negative, so we might have to deal with that. On the right side, we've got the kt plus c1. Before you exponentiate, it's a good idea to simplify the left side. The properties of logarithms, you can bring the 1/5 up into the powers, and you can also use the fact that the difference of two logs is the log of their quotient. You can write it like this. I'm wondering if something's wrong, because usually you don't get the 1/5 power like that.
Couldn't you just keep the 1/5 outside of the ln and do 1/5?
You could, and maybe I should just multiply both sides by it instead. That would be simpler. If you keep the 1/5 outside, I can multiply both sides by 5 and have a 5kt plus, let's call it C2 instead of C1. C2 would be 5 times C1. So yeah, that sounds like a better idea. Multiply both sides by 5, essentially, and write the C1 instead as a C2. I don't want to write K2 or something there. K is the original K in the problem. I want to keep that there. So I do want to write that as 5K instead of K2 or something. Now exponentiate. You get the absolute value of p over 5 minus p, and it's going to turn out, okay, I'm not justifying this, that you can get rid of the absolute value signs. And ultimately solving for the answer. Here I'm going to use the properties of exponents again to write it a little differently. Bring a c out in front. Essentially, c is e to the c2. Or maybe I should say plus or minus e to the c2 to allow for negative possibilities. You might say getting rid of the absolute value signs, maybe I need to justify it like that. Now solve for p. It's a bit tricky. Cross multiply, so to speak. If you want to think of this as being over 1, or perhaps better, just multiply both sides by 5 minus p. P is 5 minus p times that. Let me expand a bit. 5c e to the 5 kt minus pc e to the 5 kt. The goal is to solve for p, so get the p's on the left side. Like this. And then just divide both sides by this to solve for p. Question? Do you have a question? No? Okay. P looks like it's 5c e to the 5 kt divided by 1 plus c e to the 5 kt. That's okay to leave it like that. Oftentimes people simplify a little bit by multiplying the top and the bottom by e to the negative 5 kt. You could also write this as 5c over e to the negative 5 kt plus c. That would be okay as well. If I had an initial condition like p of 0 equals 0.1, representing 100 rabbits, 0.1000 would be 100 rabbits, I could solve for c. I'm not going to take the time to do that. I plug in 0.1 for p and 0 for t. E to the 0 is 1. I guess it wouldn't be too bad. Let me do it quick. E to the 0 is 1, so I would get 0.1 equals 5c over 1 plus c. This is 1/10. This is equivalent to 50c equals 1 plus c, so 49c equals 1. It looks like c is 149. Does that look good to people? And then I could plug that in for c. Question?
Yeah. So, what is it that we're given and what is it that we're trying to find in terms of population of rabbits?
Well, we're trying to find a function whose graph looks like this that might model the population.
Okay.
Here's the differential equation that we think is going to produce a graph like that for a solution. And we do the separation of variables to solve for the solution. We get a function like this as this general solution. If you add an initial condition like this one, you can solve for the constant, giving you one unique solution. Then the question is, does the graph of this look like that?
Oh yeah, so that graph hopefully will look like that.
Yep. It doesn't, by the way, all this doesn't mean it's necessarily super accurate in modeling the population. It's just a good guess, you might say. Question?
How did you get the first P and have it written in the second? Like with the 5C and
From here to here?
no, end up being the circle
From here
to the at the end.
to that?
No, the 5C.
Oh, I multiplied everything by e to the negative 5 kt
Oh, okay.
on the top and bottom, which is like multiplying by 1, so it's okay. It's almost quiz time, but let's see if we can make a graph of this to confirm that the graph looks the way it should. I'll go ahead and plug in the c equals 149 in there. So I think I'll write it in as the second way. So I'll get 5c is 5 over 49 divided by e, which you have to type in as a capital E, to the negative 5 kt. I didn't say what k is. Let's pick 0.02 for k. Just to make something up. Let's see what the graph of this looks like. There it is. Looks good. Okay, so that's a very quick introduction to differential equations, exponential and logistic model. This is not the only time we're talking about this. If you felt confused, we will come back to it. Okay? But I wanted to show it to you as an application of separation of variables and ultimately partial fractions. Let's take the quiz now.